In this video, I will be talking about inferential statistics, and in particular how you use a sample mean to predict the population mean or to infer the population mean. So our starting point is a concrete example. Let's take the example of, let's say, all Leaving Cert higher maths marks in the country in a particular year. And in that example, what we're going to do is we're going to try and predict what the mean mark is for the whole country by just using a small sample of those marks. And that's what this is all about, really. And we need some terminology to get us started as well. So the word population, we need to be precise about what that means. Population means everybody or everything we're interested in. So in this example, it will be all the higher level marks in maths in the country in a particular year. A variable is something that changes according to each person. So for example here, the variable is the Leaving Cert maths mark. That varies from person to person. A sample then is a small sample of all those thousands of students who take the Leaving Cert maths every year. So in a particular year, just take a small sample of those students, for example, 30 students. And the statistic then is the thing we're interested in working out from the sample. So for example, the statistic could be the mean mark in the sample, the mean mark in Leaving Cert higher maths in that sample of students. Then there's the parameter. And the parameter is the equivalent of the statistic, except it's in the whole population. So the parameter is the mean mark in the whole population of students, and that's what you're trying to figure out. So the basic idea here is you're working blindly with one sample of 30 students, and whatever mean you get for that sample of students, you're going to use that mean to predict the mean mark for the whole population, which we call the parameter. The mean mark for the whole population is the parameter. So ideally, if this is going to work, as you can imagine, the sample has to be what we call representative of the population. What that means is it has to be a good sample of 30 students. It would be no good, for example, picking 30 students from one school, because that school could be above or below the national average, for example. So you're better off to pick, we'll say, 30 random students around the country, different parts of the country, evenly spread. And when you do that, it's called a representative sample. Of course, the opposite to that, a bad sample, would be what we call a biased sample. Okay, so let's take the example again and take it a bit further. Imagine in the whole country, the mean mark in maths is 70%. So we use mu for short, Greek letter mu for the mean. And the standard deviation, which basically measures how spread out the marks are, is 8 for the whole country. So population mean is 70, standard deviation is 8. Now, imagine you just go around and pick, so this is thousands of students. So in this set of students here, the whole population, you might have 30,000 students, for example, or more. And we're going to take samples out of that population of about size 30 each. So here's one sample, another sample, another sample, and we could take hundreds of samples like that. And what you'll find is this: if you do it right, every sample should basically represent the population fairly accurately, most of them anyway. So here's one here, for example, the mean mark. So for mean of the sample, we use x bar. By the way, for mean of the population, we use mu. So the mean of this sample here, for example, is 67. The standard deviation is 8. So as you can see, not too far off the overall population. So with just that 30 students, you could predict the whole population if you use that sample. You wouldn't be too far off. And that's the whole idea. Again, in these questions in the exam, you're normally working blindly with a sample. You just have one sample to go on. And you're using a sample of 30, for example, to predict for thousands, maybe 30,000 students, what the result is. That's the idea. So you only ever have one of these samples, and you do your best with that sample. Now, there are other samples as well, of course. Some samples are very accurate. You might be lucky with this one. It might be exactly 70, which is the exact mean for the population. Standard deviation isn't too far off either. That means how spread out they are. As you might expect, the marks in a sample are just as spread out as the marks in the overall population. The spread is about the same, so that's why the standard deviation would be roughly the same as well. So now, the key thing now is that it turns out if you take enough samples, if you take hundreds of samples, what's the most frequent mean that turns up in a sample? And as you can imagine, again, the most frequent mean that turns up in a sample is 70 itself, which is the mean of the population. The next most common mean, I suppose, would be on either side, 69 or 71. And it trails off then as you go below or above that. So this is a key observation about this. If we go on to the next page and just state that explicitly, it turns out, and there's a theorem backing up all this. We don't have to go into the theorem in too much detail in our course. Just be aware of that it exists, really, the central limit theorem. But what it says basically is this. The mean of the whole population is called mu, and the mean of a sample is called x bar. Now, if you take lots of samples, the means of the samples themselves form a normal distribution around the mean of the population. And so what that means is the most common sample mean will be the same as the population mean, basically. And it trails off after that on either side, and it follows a normal distribution. And if the population itself is normal, it traces that, as I said, that distribution itself. Even if your population is not normal, the means still form a normal distribution as long as your sample sizes are greater than 30. So all this comes out of the central limit theorem. It turns out as well that the sample means, if you take all the sample means together and if you show their distribution, how common every individual mean is, how often it turns up, you'll find that they are not as spread out as the marks themselves in either the population or a sample. It turns out that their standard deviation is actually the original standard deviation over root n, which is the sample size. And we call this standard error, sigma x bar. So it's hard to understand what all that means unless you see something concrete to illustrate what's going on. So I've done this simulation here, and I've done a separate video on this simulation if you want to see it on my website. But for now, let's just take this snapshot here to show you what I'm talking about. What I've done in this simulation is I've done a simulation of the actual problem we're talking about. In other words, I have generated 30,000 marks, random marks, for all the students in the country taking maths. And it's centered around a mean of 70 with a standard deviation of 8. So every box here is basically a student's mark in the country. And as I said, there's 30,000 boxes altogether. So I've about 1,000 rows of 30. There's 30 in each row. Now, if you actually, the computer does all the calculating and it does all the graphing, the computer graphs the distribution of the population. So all these 30,000 students, if you graph them, the most common mark is in around the 70 in the middle, and it trails off at either side. So that's the population distribution. As we said, the mean is 70, the standard deviation is 8. However, if you took one sample of 30, and I mean any row is as random as anything else, so you might as well take a row of 30 that's as random as any other 30 numbers on the computer. So take that first row, and I've worked it out here on the computer. That first row has a sample mean of 72, a standard deviation of 6.81. As you can see, one sample is not too far off the population itself. Take a second sample. Again, you'll find 71, 8.96. Again, not exact, but they're not too far off, again, the sample, the population. Now, there is a difference, however, when you come to the sample means themselves. Take all these samples and work out their means. And instead of going along by the rows, go vertical here. How spread out are all these sample means? As you can see, they're not spread out. They vary around 70, maybe down to 67, up to 73 or 4 maybe. But they don't go too much below or above that. So these are much more tightly bunched than the individual samples themselves or the population itself. So that's a key observation. And how bunched they are is measured by standard deviation. And they have their own standard deviation. It turns out to be much less than 8. It's actually 8 over root 30. It turns out to be, you don't need to prove this, but 8 over the root of the sample size, which is root 30. It turns out to be about 1 point something. So it's a much smaller standard deviation, a much smaller spread between these marks as opposed to in any individual sample or the population itself. And there you can see the computer has generated the graph here for us of this column here. All those means. 70 is the most often that turns up, the most common sample mean, and it trails off at either side. So big difference between this graph and this graph. This graph represents the population or a sample. They're roughly the same. Whereas this one represents all the sample means. So we can summarize all that with the following table. If you take the population graph as we saw above, the mean is mu, standard deviation is sigma. It follows a normal distribution. If you take one sample, the mean is x bar. And ideally that should be close to mu as well. That should give you a good estimate of the actual population mean. Also, the standard deviation of one sample is more or less the same as the standard deviation of the population. As a matter of fact, in exam questions, usually you only have the sample standard deviation, and you can always assume the population standard deviation is roughly the same. And lastly then, all sample means, this graph here, they have the same mu, They're centered around 70 still. The difference is they're much more tightly bunched, and their standard deviation is much tighter. It's sigma over root n. It's a much smaller number. And it's called sigma x bar, or it's called standard error. Okay, so moving on. We now want to talk about the concept of confidence intervals. So again, let's take a real-life example to illustrate what this is. This is a Premiership League table, just taken from the 2020-21 season. And it's roughly halfway through the season. So all these teams have half their games played roughly, and they've another half to go. And if you're looking at, say, for example, Manchester City, who are on top right now in that table. If you were to ask somebody neutral, I mean, where you expect Manchester City to finish based on that at the end of the season, I think you'd be fairly confident that they will finish high up anyway. Let's make a prediction. Let's say we're about 50% sure that they will win the league. We'll put some numbers on this. You could be a bit more confident, of course, that they might finish in the first two. I mean, they might slip a bit, but they could still finish in the top two quite easily. So you're more confident there. Let's put a number on it, maybe 60%. You're more confident again they'll finish in the top three, obviously. That's 70%. And so on up to, for example, in the top 10. It's fairly unlikely at this stage, if they've done this well so far, that they'll drop anywhere below the top 10. So you could put a number on that. Maybe you could be 95% certain, if you're betting on this, that they will finish in the top 10. And that's all a confidence interval really is. If you kind of show this graphically, this is the first spot in the league, first and second spot, first down to the 10th spot. So these are like your intervals, your confidence intervals. So you would be, for example, 50% confident that you'll finish in the top spot, but you'll be a lot more confident, 95% confident, that you will finish between 1 and 10. So that's your confidence interval, and you're 95% confident of that. So the key observation here really is the less specific you are, the more confident you can be that you will be correct. That's the basic pattern here. So that's the way it works in our questions and statistics as well. We're going to build confidence intervals, and we're going to make predictions. So the idea always, as I said before, is we're taking a sample, we're working blindly with that sample. We're going to use that sample to make a prediction about the whole population, and we can make that prediction with a certain degree of confidence. In our case, we will always use 95% confidence intervals. That's the only interval that's on the Leaving Cert exam. So we'll work out this interval now for the sample mean example that I've just been talking about. So what you do is you go back to your definition of z-scores. Well, a z-score is always how far along the normal distribution curve are you, to the left or right of the mean. Well, the z-score gives you that. So in the case of sample means, the sample mean, if you take a given sample mean x bar, well, that minus mu over the standard deviation of the sample means, that's your z-score. But as we saw earlier now, this sample mean, of course, is much tighter than the population, so it's sigma over root n. So there's your formula for the z-score for sample means. And that formula is in the tables. Now we can rearrange this, multiply across by what's below the line here, and you get z times this equals x bar minus mu, or rearranging again, get mu on its own. Mu is x bar minus z times sigma over root n. Now, the next point we want to make is this. Just say if we graph, this is a graph here of your mean, of your population. So this is the world from the point of view of the population. The population mean is here, and all the sample means are on either side, trailing off in each tail here. And let's pick a number, 95% of all our sample means. So that's the number we go with always in this course. If you want to find out where 95% of your sample means are in relation to the actual population mean, well, you figure out the proportion that you need here. So working it out, if you 0.025 or 2.5% down there and 2.5% up there in either tail, that means that there's 95% in between. And so these are the two important lines now. These are the two important points, the 2.5% in this tail, the 2.5% in the upper tail. And 2.5% corresponds to a decimal of 0.025. And up here, if you come down 2.5 from 100, you have 97.5 or 0.975. Subtract these two numbers to find out what's in between, and there's your 95% confidence interval. Now, what's significant here is if you use your tables to get the z-score, the corresponding z-score, for that, for these proportions here, 0.975, that corresponds to a z-score of 1.96. And 0.025 corresponds to a z-score of minus 1.96. So now this number 1.96 becomes very important from now on when you're talking about the 95% confidence interval for sample means. And so 1.96 is basically the limit of your confidence interval, and minus 1.96 is the limit at the other end. Of course, you can go from that then back to a z-score using the z-score formula, or sorry, to an x-score as we call it, or an x-bar score. And that's what we're doing up here. If you bring this back to here now and work it out as an actual sample mean, what do you get? Well, as you can see up here, if you put your z equal to 1.96, which is the limit of your confidence interval, you now have your confidence interval becomes mu plus or minus 1.96 sigma over root n. So 95% of all your sample means are in that interval. You can also say it the other way around. If 95% of all your sample means are in that interval, well, vice versa, if you just work from a sample mean, if you're working blindly from one sample mean, you can be 95% confident that the population mean mu is in this interval. You can say the same thing the other way around, basically. And that's what we call the 95% confidence interval from now on. So in reality, you're working with one sample usually in a question, and the sample has a sample mean of x bar. So the confidence interval for that, the 95% confidence interval, is x bar plus or minus this. In exam questions, the 1.96 part, the 1.96 sigma over root n, is often called the margin of error, or the radius of the confidence interval as well.